All right, today we're going to talk about isotopes. So one of the things we're going to talk about with isotopes is remember that when we look at, for example, the element carbon, or let's say chlorine, Cl has 17 up here, and then sometimes the box will have the name in it, and then it'll have 35.453 down below. Okay? And that number down below, the 35.453, is what we call the atomic mass, the molar mass, and now we're also going to call it the average atomic mass. Okay? Because what exists with chlorine is chlorine has basically two main different what are called isotopes. Okay? And an isotope is nothing more than an atom that has a different number of neutrons in it. So atoms with the same number of protons and electrons, but a different number of neutrons are called isotopes. So for example, there are two naturally occurring isotopes of chlorine, which means of the chlorine atoms that just naturally exist in nature, there's some of them, just that's how they are. Some of them are chlorine, and we call it chlorine 35. And what that means is it means, okay, well, chlorine, again, 17 protons. Okay, we know that never, ever changes. Okay, so that's 17 protons. How many neutrons is it going to have? Of course, it's going to have 18 neutrons because 35 minus 17 equals 18 neutrons. Okay, but one of the other isotopes that exists of chlorine is chlorine 37. Okay, and again, how many protons does it have? That never ever changes. 17 protons. How many neutrons does that chlorine atom have, though? Is 37 minus the protons, which is 20. So some of the chlorine atoms that exist in nature have 18 neutrons. Some of them have 20 neutrons. Now, why? Isn't that the great question of the universe? Why? Where did this all come from? All of that? We don't know. That's just how chlorine is. Some of the chlorine that exists in the world has 20 neutrons. Some of it has 18 neutrons. And what this number is, which we'll talk about in the next lesson, is an average of those two numbers put together of that 35 and that 37, which we'll talk about later. Now, how do we know that there's some chlorine that has 18 neutrons and other chlorine atoms that have 20 neutrons? Is because of a device called a mass spectrometer. Okay, a mass spectrometer shows you the different isotopes of that element, and it shows you how much percentage-wise you have of that element, etc. Okay, so let me just show you one here. Here it kind of explains how it all works. Not a big deal. A mass spectrometer, and this graph, this is a graph of the mass spectrometry data table here, shows us that according to this information, this element has 1, 2, 3, 4, 5, 6, 7 different naturally occurring isotopes. So you take a sample of that element, you put it into this machine, it does its thing, and then it spits out this data that says, okay, of all the atoms of, in this case, a pretend element, Y, these are the different masses that we found. We found, again, this is estimate here, about 15% right here contained a mass of 92. About 10% had a mass of 94, etc. Okay? So there's a lot of things you can tell from this graph. You can see, number one, how many isotopes are there? How many isotopes does this atom have? It has 7 different isotopes. Okay, it also shows you which one is the most abundant. Well, clearly the tallest one on the graph, that 99 there, the 99 isotope of Y is the most abundant isotope. And we can even do some math with this, which we'll do in the next lesson. Okay, so let's look at an example of this. So we can see there's 7 different isotopes. We can see that, again, they all have the same number of protons, but they all have a different number of neutrons. Which one has the most neutrons? Well, clearly the one that has the greatest mass, because the protons don't change, so the neutrons do have to have changed. So this one, A, has the fewest number of neutrons, where D has the greatest number of neutrons. All right, Based on the mass spectrum of atom Y, which of the following statements is false? I don't like these because I like looking for the right answer. Now we got to look for the wrong answer. So A says peak A, so this one, and peak D come from atoms that have the same number of electrons. Remember, isotopes have the same number of protons and the same number of electrons. It's only the neutrons that have changed. Remember, the electrons weigh so much less than the protons and the neutrons that they don't even count anyway in terms of the mass. Okay, so do peak A and D come from atoms that have the same number of electrons? Of course they do. Okay, if you change that word right there from electrons to neutrons, then that's false. Okay, letter B, there are 7 isotopes of atom Y. 1, 2, 3, 4, 5, 6, 7. That is true. Letter C says peak C comes from the most abundant isotope of atom Y. Whichever one's the tallest, that is the most abundant isotope. Absolutely, that is the tallest one. That is true. Okay, and then letter D says peak D comes from an atom with 4 more protons. Again, protons don't change. That is the correct false answer. Okay, example 2. The identity of compound Y is... Oh, so it's not a fake element, it's a real element. So what we need to do then is to know this is we need a periodic table. So I'm going to pull up a periodic table here. If you have one in front of you, great. If you don't, you absolutely will need a periodic table to do this. Okay, so again, let's try to again ballpark it here. When we look at just want a regular old periodic table here. Nope, that one doesn't have masses on it at all. That's not helpful. That one also, no. Holy cow. It should not be so difficult. Okay, here's one with masses on them. So we know that this element, whatever it is, must have a mass between 92 and 100. Because remember that when you take all of those isotopes and put them together, you're going to get an average. Okay, so if you take all of those masses, and considering that C is the highest, and you kind of averaged all those out, where would you be more or less in terms of the average atomic mass? Again, I'm kind of 92 and 100. So if it was right smack dab in the middle, I'd say 96. Okay, and right at 96, this one's a little bit higher than all the other ones. So I would say probably in this region right here is a good one. Okay, so now I'm going to go to the actual periodic table here. And I can look and see here that niobium has a mass around 92.9. Is it probable that the average atomic mass is here? No way. Average all those together, there's no way it's all the way down by 92. Okay, and then we go all the way up to technetium, and it's up in the 98, 99 region. So now we're way up over here. But right in between those two is the element molybdenum, and it has a mass of, you can see here, 95.95, and that is certainly that element, looking at masses, is the closest to, again, this general area right in the middle. Okay, so I would absolutely choose molybdenum there. Okay, and then example 3 says, which peak comes from an atom with the greatest number of neutrons? Again, the protons don't change, but the neutrons do. So which one has the greatest number of neutrons is the one that is the heaviest. Okay, so therefore D is the correct response. Okay, example 4 says 3 possible mass spectra for a sample of atomic iodine. So I'm looking at iodine on the periodic table. Iodine has a mass of roughly 126.9 is what I've got based on that periodic table. Okay, and then it says identify the mass spectrum that represents the isotopes of iodine, and then justify your choice. Okay, so now we're kind of looking at how tall are these peaks. For example, if you average, let's look at this first one here, spectrum A, and you put those two together. Again, it's not just, well, one's 126, one's 27. They meet at 126.5. It depends on how tall the peaks are. Since that peak is so much taller than this one, the average of those two are going to be really, really close to 126. Okay? These two, spectrum B, because they're both 50%, then absolutely yes. What's the average of those two? Would be right smack dab in the middle at 126.5. So this one would have an average of around 126.1. This one would be around 126.5. Whereas this final one, because again, 127 is much, much taller than 126, you average those two together, you're going to be much closer to 127 than you are 126. So that's where you come up with your 126.9. Okay, so in this case, I would answer spectrum C, and then I have to justify my choice. If I just write spectrum C, they're not going to give me credit. So I would say the average of the two masses is closest to the average atomic mass of iodine, and you might even put in there 126.9. Okay, and again, clearly you are telling the grader, I know what I'm talking about, I know why it's spectrum C, and that absolutely you would receive the point for that. Okay, now remember that earlier we had talked about the John Dalton, and these are kind of his original ideas, and he had originally said that all atoms of an element are identical, but now we know that that's not true, because the neutrons are many, many times, like chlorine, for example. Chlorine has two, one of them's about 75%, one of them's about 25%, so that means there's a lot of variation in the chlorine atoms that just naturally exist in the world. So no, all atoms of the same element are not identical. We know that, okay? What we do know is that atoms, and remember, we're talking about protons and electrons here. We're not talking about ions, we're talking about atoms that are neutral. So all atoms of the same element do contain the same number of protons and electrons. That's true. If you change the protons, you change the element. But because we now know about isotopes, isotopes do produce a different number of neutrons. And almost every element has a different number, has different isotopes. Okay, even hydrogen, there's three different isotopes of hydrogen. There's the normal hydrogen that has has no neutrons, but then there's one that has one neutron, there's one that has two neutrons. Okay, carbon's the same way. The most common isotope of carbon is carbon-12, but there's also a small amount of carbon-13, and even in our bones, the way that they determine how old bones are is they use carbon-14. So most carbon has 6 neutrons, but a small amount of carbon has 7 neutrons, and an even smaller amount has 8 neutrons. Okay, and this is all based on your ability to look at a mass spectrometry graph and know that anytime it talks about the mass spectrum of something, you're simply talking about the neutrons and therefore the different isotopes of that element. And right now you're like, well, this is easy. Well, once we start learning about other graphs, they all kind of get jumbled together. So remember that with mass spectrometry, we're talking about isotopes that have a different number of neutrons. Okay? And then the final thing that we'll talk about today is that remember that when something chemically reacts, that it's the electrons that are typically what are changing. They're sharing, they're transferring, etc. Okay? So when you have two different isotopes of, let's say, chlorine or carbon or something like that, they typically have the same chemical properties, which means they react in a similar way to each other. So whether it's chlorine-35 or chlorine-37, the way that chlorine reacts depends on its electrons, not on the number of neutrons that it has.